Animatable body 2D. To demonstrate this node, I have created a simple scene with an animatable body 2D and a static body 2D to act as platforms, and of course a player controlled character body 2D. So let's see how the character body 2D interacts with the static body 2D. Both static body and animatable bodies cannot be moved by external physics forces and have to be moved by code. The static body can push the player around, but the player cannot stand on it. The animatable body, on the other hand, estimates its linear and angular forces to move other bodies which are colliding with it, making it a perfect dynamic platform which can be used to travel on it. CanvasGroup. According to the documentation, the CanvasGroup node is to blend translucent texture smoothly, like this and not like this, where you can see the overlapping area very clearly. To do so, you have to alter the self-modulate property on the CanvasGroup node. If you try to alter the modulate or any type of modulate properties on the individual children, you will get this added blend again. I also had the suspicion that, similar to how multi-meshes work, the CanvasGroup might speed up the drawing of textures, so I did some test runs and checked if there were any noticeable results, but there really doesn't seem to be a major impact. But please keep in mind that this is not very scientific, and before drawing any conclusions I suggest you test this for yourself. Directional light 2D. The directional light 2D simulates light as a straight line, similar to how the 3D directional light or the sun and Blender work, only in 2D. Like the normal light, it is affected by light occluders and normal maps. You can set colors, shadows, shadow sharpness, shadow color, blend modes and a lot more to really spice up the visuals of your game. Shapecast 2D. The Shapecast 2D is basically a raycast 2D, but instead of a thin line, it casts shapes along a line so that you can easily simulate, for example, a laser which is broader than just a thin line. It works similar to the raycast and it can hit multiple targets at once. Animatable body 3D. The animatable body 3D works exactly like the animatable body 2D. You cannot push it around with physical forces, but only in code or through animation. But unlike the static body 3D, it applies its own estimated linear and angular forces to bodies which are colliding with it, making it again useful to act as platforms, for example. Decal. Decals are non-destructive texture projections on a mesh. In Godot, the texture's appearance is affected by position, rotation and scale of the decal node. The texture can have an additional normal, arm and emission texture. Upper and lower fade affect the texture's transparency when it comes closer to the top or bottom of the box that surrounds it. A decal can be applied on multiple meshes at the same time. If you don't want this to be the case, you can use the Decal mask property on the decal and the visual instance layer in the meshes to only apply the decal to certain meshes. FogVolume. FogVolume is a node which creates fog within a defined shape. For this node to work, FogVolume in the world environment needs to be enabled. It has properties you would expect from a fog, like color, density, how it fades towards edges of the containing shape or with increasing height, and you can even go with negative densities to subtract fog from other fog volumes, or even the global fog, be it set in another fog volume or the world environment itself. Importer Mesh Instance 3D. What can I say except there is nothing to say. Nothing is documented, and when diving through the official Godot repository, it looks like this guy is only used when importing scenes or meshes from GLTF, OBJ or Collider DAE. GPU Particles Attractor Sphere 3D, GPU Particles Attractor Box 3D, GPU Particles Attractor Vector Field 3D, GPU Particles Collision Box 3D, and GPU Particles Collision Sphere 3D. Phew! Primitive GPU Particles Attractor bodies come in box and sphere shapes, which apply forces to particles that enter the volume. You can adjust the strength to attract or push particles away, define direction and how the forces fall off further away from the origin. Keep in mind that for this to work, collisions must be enabled in the process material of the particles node. New are also particle colliders. Primitive particle colliders come in a box and sphere shape, even though there are more complex versions later on. And they do exactly what their name suggests. They are physical obstacles for particles and let them either bounce off or disappear completely, depending on the configuration of the node. For both colliders and attractors to work, you have to make sure that they intersect with the visibility AAB of the emitter node, or else they won't work. The vector flow field is also a particle attractor, which interacts with particles based on a texture resource. In my example, I have only applied a noise texture, which is 1 by 2 pixels, one white, one black, which results in the vector field pushing particles away in two opposing streams. GPU particles collision height field 3D automatically creates a height map to calculate colliding shapes based on meshes. It is required for these meshes to be contained within the height field size. You can control when the height map should be updated, be it always or only when moved to save performance. This node has an attach to camera option, which will make it follow the camera even if it is not a direct child of it, making it perfect to simulate particle collisions only close to where the player can actually see. GPU particles collision sign distant field 3D. The particles collision SDF works almost exactly like the previously explained particles collision height field, only that it does not update in real time and needs a baking step. You just have to make sure that everything you want your particles to collide with are again contained within the particle collisions node size and hit bake. And also there seems to be an issue with actually displaying the baked behavior because for some reason it does not properly update in the editor unless you reload the current project. LightmapProbe. I swear, creating this demo for this node took me probably longer than all other demos combined, because while the documentation explains what the node does, it never says how you actually set it up, so I thought a real guessing game for a while. Also, I want to give a huge shout out to the YouTuber Brekkies, who released a Unity tutorial about light probes, and while it did not solve my problem of setting them up in Godot, this seems to be one of the best explanations of light probes I have so far come across. Now back to Godot. For this light setup, it is important that the light has a bake mode set to static or dynamic. When I tested it, it worked with both. All meshes need to be UV unwrapped. If you use Godot inbuilt meshes, you can check the add UV2 options in the mesh resource. And the global illumination modes on the static meshes, so the walls and the floor in this example need to be set to static. The moving sphere is dynamic in this case. In this demo I have a blue and a red floor and a directional light right here. I also use a lightmap GI node because the LightmapProbe to my knowledge only can be used in combination with this node. When baking a lightmap, the lightmap node will automatically generate probes. To minimalize that, in my bake settings I have gen probe subdiv on disabled, which means there will only be one probe per corner of the lightmap GI box. So if we hit bake and select the lightmap node, we can see that the generated lightmap probe in this corner is colored in red. This is because on the position of the probe, the reddish indirect lighting hits the probe itself. If we now move the dynamic body between the red and the blue floor tile, we see that there is no indirect lighting at all affecting the sphere. But see what happens when we move it close to the lightmap probe. The sphere will suddenly receive the same reddish indirect lighting as the generated probe. And I think you already know where this is going. If we are now going to increase the gen probe subdivision and rebake the light map, you can immediately see that our scene is flooded with probes, and if you look closely, then you notice that every probe has its own correct indirect lighting. The ones on the right get the bluish indirect light from the blue floor, and the ones on the left get the red light reflected on them. And if we now move the sphere between the two spots where the floor transitions in color, you can see the real magic happening, because we have indirect lighting from a static light map affecting a dynamic body. One downside of the increased subdivision though is that we now have our probes evenly distributed, even though we technically don't need them to be this dense on places where you do not need details so accurately, like for example the center of the blue or red floor, because for each there is only one color affecting the sphere at once. To give you control over how these probes are distributed, you can manually add lightmap probes nodes and rebake the light map. When baking the lightmap, manually placed probes will also get lit by indirect lighting and affect other dynamic bodies, exactly like the automatically generated ones. Shapecast 3D. The Shapecast 3D is similar to the normal raycast, only that it ends with a custom shape, like for example a sphere in this case. This also enables it to occasionally register multiple targets at once. ShaderGlobalsOverride. The ShaderGlobalsOverride behaves similar to a world environment, only one at a time can be in effect. For this example I prepared a very simple shader which colors a texture in a color which is set as a global shader variable. If I want to add a second global variable directly in the shader editor, you will see that I get an error. This is because shader globals have to be defined in the project settings, and there you can already see the global color variable, which is set to 1111, which is basically just white. I could theoretically also just add the new variable and the error would go away, but I will just remove it from the shader entirely. When I now go back to a ShaderGlobalsOverride node, you see that our defined globals show up in the params section. Similar to the world environment node, this yellow warning triangle means that there is already a ShaderGlobalsOverride in effect and that the second one has basically nothing to do. So if we inspect the one which actually works and check our global variable in the inspector, you see the texture disappears. This is obviously because the new shader global is overridden with 0000, which is basically a fully transparent color. MultiplayerSynchronizer and MultiplayerSpawner. Considering that this demo now involves networking, making everything exponentially harder to understand, I will follow this demo up with a little animation which is going to explain the core elements of those nodes again, because even this minimal demo might be hard to get. Short overview: the MultiplayerSpawner is a node which gets a path to another node in the tree, and whenever certain scenes are added to this selected node, it will be added on all other connected peers. Here I have prepared a very simple scene with a host and join button for multiplayer and a MultiplayerSpawner node which has the spawn path set to the scene's root node and which has a path to my player scene added to its auto spawn list property. This setup means every time a scene which is contained in the auto spawn list gets added as a child of the node set in the spawn path property, it will automatically be instant on all connected peers. The ready and physics process are collapsed as for now, because they don't do anything by now and I will use them to show how custom spawns work later on, but now they could as well not be present. The character scene is a simple character body with a sprite and the new MultiplayerSynchronizer node. This node is used to synchronize selected properties of a node across a network. If we inspect the MultiplayerSync node, we see the root path is set to the character, which means that those two properties will be synchronized using custom intervals from the node settings. The player scene only allows the right client to move it, so that one player is not controlling the other characters of course, and in addition every not player controlled character is colored in red. So if we start two instances of our game and connect them to each other, you can see that every player gets his character spawned in and that rotation such as position are synchronized. If I delete the rotation track from the replication tab and restart everything, you will see that obviously rotation is not getting synchronized anymore. Now let's lift the secret behind ready and the physics process method. Since the automated spawning via the MultiplayerSpawner might be too primitive for some cases or for most cases where more customizability is required, you can also create your custom spawn methods. For this you have to override the MultiplayerSpawner spawn function method with your own custom method, which takes up to one argument and has to return a instantiated node which is not inside the scene tree, and also make sure that the path to the scene you want to replicate is not set in the auto spawn list property of the MultiplayerSpawner. One difference now is that instead of manually adding the scene to your tree and letting it automatically be replicated to other peers, you just call the spawn method with your custom data as an argument, and the MultiplayerSpawner will add the scene locally and on all remote peers. Let's say this is our setup. A scene with a node 2D as a root node and a MultiplayerSpawner as a child. The spawner spawn path property references the node 2D and the auto spawn list has one element, namely the path to a character scene in our project. In the previous demo, The multiplayer synchronizer had position and rotation of the character body tracked in its replication tab, even though in this example I'm focusing more on the spawner, just a side note. Now let's say we have two players with this setup who are simply connected over the Godot multiplayer API, making one the host and one the client. Both are running the same project and have the exact same scene tree setup. And if we rewind a bit, then we remember that both multiplayer spawners have their local root node 2D set in the spawn path and the local character scene in the auto spawn list at the same index. If the host now instantiates the character scene and adds it as a child of the node 2D, then the multiplayer spawner of the host realizes, hold up, did a scene from my auto spawn list just get added to my spawn path? Yes. So now the spawner from the host sends this data to the spawner of the client, which it can identify because the remote receiver node is on the same path as it is on the receiving side. The data sent includes that the scene with the index 0 in the auto spawn list of the sender has been added. So now we look at what happens at the client side. The multiplayer spawner takes the index received, in this case 0, and gets the scene which is at index 0 in its own auto spawn list, which means that the receiver doesn't actually know which scene was instanced on the sender. It only knows that it had the index 0 on the sender, so it also takes its own index 0, which could theoretically be a whole other scene though. This scene is then loaded from the local project and added to the spawn path property of the receiving multiplayer spawner node, which doesn't necessarily have to be the same as it is on the sender. It is also possible to have particle collisions in 2D. All you need to do is set the collision mode in the particles material and use a light occluder as an obstacle. In my previous all nodes video, the new navigation nodes were only lightly documented and a mystery to most, including to me, which is why I want to redo especially the navlink nodes in this part. In this demo we have two navigation regions with navigation meshes which are not connected and two navigation links set on unidirectional, so only traversable in one direction, in this case from the left to the right. The entry points are both marked with the Godot icon, and of course we have a character which will navigate through this scene with the help of the navigation agent. Running the scene you can see that whenever I click a place, the character calculates the fastest path and moves along it. Navigation links have a enter and travel cost of 0 in this example, which means that the character treats them basically as immediate teleports and therefore moves to the entry of 1 when the move to point is close to the navigation link's exit. Usually you would actually place an area at the entry of the link so that you can actually teleport the character, because on reaching the entry it will just normally travel along the line until it reaches the exact exit of the link. Also, when looking at the underlying navigation mesh, you can see that it is split into those different colors. Apparently these are not just visual, but also have an effect, because when using the navigation link with the beginning and the exit in the same navigation region, the navigation link won't work when the region is just one solid shape. This was a real problem with the game I'm currently working on, because I just had one supersized square as the background for all characters to navigate on, and I couldn't figure out why the navigation link wasn't working. But when I split it up in multiple regions, everything started to work fine. In this demo you can see how the character cannot traverse the distance between the two navigation region nodes. You can edit the connection margin in the project settings so that regions which are farther away from each other become automatically connected. This demo consists of 3 platforms, one of which travels between the other 2 and lets the character body traverse, and which has its own navigation region. The other 2 platforms have their own navigation region and are child of the same region, so if we hit bake on the navigation region, both of them will receive a part of the baked navigation mesh. The character body will always try to catch the camera, And at last we also have a navigation link, of course, which has its entry point on the platform the character starts at and the exit on the other static platform. The purple square you see on your screen is a visualization of a connection between two different regions. You can change the edge connection margin in the project settings. If we hit run, you see the player walking onto the moving platform, trying to chase the camera, but because I'm stupid, this bozo fell off the platform, so after I fix this you can see how the character tries to catch the short time window where the last platform and the moving one are connected, but because he is too slow and the connection disappears again, he will pick the next best path, which leads him to the entry of the navigation link, because the nav link's exit is very close to the camera.